Hello everyone. In this video, we are going to talk about symbolic operations in Python. And for that, you need to have a new module called sympy added to your Python so you can perform all of these operations. So here I have added sympy, and then what I need is to go ahead and just import the stuff that I need, but here, just for simplicity, I imported everything from it. So when you want to define the symbolic variables, as many as you need, you put them on the left side of the equal sign, so x, y, z, and so on, and then you use the method called symbols. And then here you see inside quotation, I wrote those names again, separated by space. If you want, you can do it one by one, but here you can do multiple assignments in a single line. And then the other parameter you have to use is called real true. What is that one? This is what we call an assumption. So here we're saying that these parameters are going to represent real numbers. You can add other things. For example, we can say positive true, right? If we say that, that means these parameters are positive. They're representing positive numbers, okay? So if you don't want, you can just go ahead and basically get rid of this. But then if you are solving, let's say, an algebraic equation and the number that it gets for x and y could be a complex number, right? Then that is basically not contradicting anything, while here, when I say they are true, then it is only looking for the real parts, the real answers, right? Instead of just anything. So here you can have some assumptions. If you want, as I said, you can get rid of it. If you want, you can do this assignment in several lines, right? So you can say x equals, then symbols of x, and then you can do the same for y, and you can do the same for z. But again, here you're doing it everything in a single line. Good. Now let's look at the operations that you can do. One of them is performing derivatives. If your function has only one variable, then you can go ahead and just take derivative, as well as if it has several variables, multivariable, it doesn't matter, you just call it partial derivative, but it is going to do just fine. And the command is diff, just like MATLAB, the command is diff. So here my function is cosine of x. I'm going to take derivative with respect to x 2 times, right? So second derivative of cosine, the first one is negative sign, the second one is negative cosine, and that's what it is. So you can take as many derivatives as you want from a function. Here I'm defining a function that has basically 3 parameters, x, y, and z. And then here I'm taking partial derivative with respect to x and partial derivative with respect to y. So let me go ahead and run this part for you. Okay, so this is that negative cosine I told you. This is that function. And now look at the derivative of function with respect to x. Of course, x cubed is 3x squared, 4xy is 4y, and then x sine of z is sine of z. And derivative with respect to y is 4x here, and then z to the power 8 here. So you see it is doing the job perfectly. You can also do symbolic integration. So you can basically do it definite or indefinite integral. So if it's indefinite, all you need is the command integrate, the function, and the parameter to integrate with respect to. So here, integral of cosine, as you can see, is sine, right? Of course it is, because derivative of sine is cosine. And then you can take indefinite or definite integral by passing the limit. So here I'm integrating exponential of x with respect to x, but from 0 to infinity. And the interesting thing is this infinity here. Okay, you don't pass INF or math INF or anything, because that's a number. You need to pass a symbolic for what? For infinity, and as you saw, the symbolic is OO. Okay, so yeah, that's an interesting thing. This OO is basically a symbolic for infinity. And as you can see, I passed the input argument as well as the upper and lower limits all in a single parenthesis, because this integrate function, it expects two inputs. One is the function, one is the rest. So here I'm combining everything into a single parenthesis, and here integral of exponential of x is, of course, what? Negative exponential of x. And you plug it at infinity, so it's going to be 0, and then you plug it at 0, it's 1, negative 1 is positive 1, which is what you can see here. If you want, you can do limits. Again, the command is basically limit. So you see these are very similar to MATLAB. Diff is diff, int is integrate here, limit is limit. So you pass through the function sine of x over x as x approaches 0, and you know this limit is 1. So you see it is doing fine. You can pass any other function that you want. So you can say, for example, 1 minus cosine of x, right, over x squared. You know this one, right, from your calc, hopefully. You know this is also 0 over 0, and you know how much this one is based on a Maclaurin series. So let me run it again and just check it. And here, let's see, how much is it? Well, here it is telling me that it's infinity, and the reason is probably the cosine is divided by x squared, not the whole thing. So I need to put this 1 minus cosine in parentheses, so the whole thing is divided by x squared. And let me run it one more time for you. And the answer is 1/2 as expected. Okay, so you see that it is doing the job perfectly fine. You can do Maclaurin series. So let's say I want to get Maclaurin series for sine of x from a polynomial with power 0, which is constant, to the polynomial of order 4, not exactly to power 4, to the power less than 4, and then from 4 and order, I use it as order 4 and higher. So here I say until the fourth order. The fourth order itself is not included. Okay, the fourth order itself is not included. Keep that in mind. So here you see that it is x minus x cubed over 6 plus order of x4 to the higher. If you want to see a fourth order, first of all, there is no fourth order. The next one is a fifth order. So if you want to see fifth order, then you have to change this to 6, right? So if you want to see until the fifth order, then you can change it to 6, and then the next term is plus x to the 5 over 5 factorial, which is 120. So let's go ahead and see that, and you can see it here, and then plus higher order terms from order 6 and above. Okay, so you see it is doing just fine for a Maclaurin series. Okay, what else do we have? One of the very important commands is subs for substitution. So let's say you have a function exponential of negative x sine of x, and you want to calculate it at x of 1. So all it does, it plugs in 1 in it, and it gives you exponential negative 1 sine 1. Now, one of the things that subs doesn't do, it gives you a symbolic value. It does not give you a decimal. Okay, it does not give you a float number. Okay, it does not. So if you really want to get the floating number, the decimal corresponding to this, you have to use the other function called dot eval f, this method. So here, the answer here, which is that sine 1 exponential negative 1, I assigned it to the symbolic variable called ff, and then I'm evaluating that with 3 decimals to a floating, eval floating 3 decimals, and you see the answer is what? 0.310. So we have subs, that gives us symbolic answer, and we can use eval f to get what? To get the corresponding float. What else do I have? So you can plug in several values if you want at the same time. So here is a function with 3 variables. And here I'm going to plug in x of negative 1, y of 2, and z of 1 all in the function. And I can do that. So the sub does not need to do one parameter at a time. If it's multivariable, I can do multi substitutions at the same time, as long as I put each one of them in a parentheses where the parameter, comma, the number is there, and then comma separated from the next one, and then put the whole thing in a bracket. That is going to do multiple substitution at the same time, and you see the number is -9 because, of course, it's very simple. What else do I have? Simplifications, which is very beautiful. So let's say I want to simplify sine squared plus cosine squared, which is, of course, the answer is 1, right? Or the other simplifications methods that are available is expand. So let's say I'm saying expand x minus 1 times x plus 1, which means multiply together and write it as a polynomial. So you see it does, and it's x squared minus 1, which is easy. The other one is the opposite of expand, which is factor. So I'm saying factor out x squared plus y squared plus 2xy for me, and you see it does it, x plus y squared. The other one, which is very beautiful, is partial fraction expansion, PFE, which is basically writing the ratio of two polynomials as the simplest form, where it is finding the roots of the denominator and then trying to write it as the summation of simpler lower order polynomials. And this is something that we use a lot in controls, in limits, and so on. And here I have this quadratic term over this cubic term, where the roots of the cubic term are, as you can see, 0, 1, and -1. And the command for it is called apart. The command for it is called apart. In MATLAB is called residue. But here, this apart command, as you can see, it is going to give us the partial fraction. So it's 2 over x plus 1 plus 4 over x minus 1 minus 5 over x. Okay, so you see it is doing perfectly fine here. And then we can solve algebraic equations, and we can solve what? Differential equations. As long as there is a solution for them, this method called solve set is going to solve algebraic equations for me. So here I'm saying x squared plus minus 3x plus 2 equals, and then solve it for x. Now, of course, when I don't put the right hand side, that means it's equal to 0. Okay, so it's basically this. And it says the roots of this are, of course, they are at 1 and 2. It's a simple equation, and it can solve it analytically. Okay, if it cannot solve it analytically, then you might not get anything. So if I say plus cosine of x, right, and then 2 times exponential of -x, I might not get an answer, right? So let's go ahead and try to solve it, see if it can solve this, which of course I don't think it can. But you see here, it says the roots of this as condition set complexes. What does that mean when you get something like this? It means, hey, sorry, I could not solve, okay? When it doesn't give you numbers, that means I could not solve it, okay? And don't be surprised. It cannot. Not every equation, algebraic equation, we can solve analytically. That's why we have the numerical methods, okay? And finally, solving differential equations. So for differential equations, we have to create what we call an undefined function first. And then we can go ahead and define the differential equation. In this case, I really do not need g. As far as I can see, all I need is f. So let me get rid of this g. I had another example following this for g. I had 2 examples, one with f, one with g, but I decided to just show you one of them to keep the length of the video short. So let me get rid of that g for you, because again, I don't want the video to be super long. So here, what I create is called an undefined function. What does that mean? It means, hey, this function f is the answer to the differential equation, okay? Like y, for example. If y is a function of x, or here f is a function of x, this f is the answer to the differential equation. I don't know what it is, so I cannot define it ahead of time like this for you. Accept it from me as an unknown thing that is still defined, because I want to define its derivatives, but I don't know what it is. So if I go ahead and say print f, right? If I say print f for me, let's see what I get. You see, it just says f. This is just f. It's an unknown function which I have to define again because I need its differential as its derivatives. And then I define my differential equation. So what is my differential? My differential is this. First of all, I put EQ, and then inside EQ, I define my equation. So we need this EQ, and then here I say what? F of x dot diff xx. What does that mean? It means the second derivative of f with respect to x. So xx is the same as x and 2. That's the same as this one. Xx means x and 2. Minus 2 times f of x dx, so minus 2f prime. So f of x dot diff. You see how it's doing it? If it's a regular function that you already defined, you don't need to use dot diff. You just say diff and then function. If it's an unknown function, undefined function, then for the derivative, you don't say diff of f, you say f dot diff. That's how you define the derivatives. Plus the f itself, and then the right-hand side equals sine of x. And you don't say equal here. You separate the left-hand side and the right-hand side with a comma. In MATLAB, you use double equal sign here. In here, you don't. You just say the left-hand side, comma, the right-hand side. And then the method is just like MATLAB, is called desolve. And you desolve that differential equation for f of x. And as you can see, it is going to give you the solution as what? As a function of two unknown coefficients, c1 and c2. So it says the solution is what? c1 plus c2 exponential of x plus what? Cosine of x over 2. This is the particular solution. This is the homogeneous solution. Right? And so if you have initial conditions, then you can plug in the initial conditions, and that is going to give you what? C1 and C2. So you see, I can easily do what? Differential equations. Again, as long as there is an analytic solution available. Otherwise, I have to resort to numerical solutions, which I demonstrated in my previous video. So hopefully this video is useful to you, and you learn that, hey, Python does have a symbolic library, which I have to install, called sympy, and I can do lots of things in it. Thank you so much. I'll see you in the next video.